Good morning. In this particular video, I'm going to discuss the properties of metal. Most of these properties, probably you have already encountered this in your strength of materials. Engineering stress, engineering strain, the modulus of elasticity, the shear modulus, and all other properties. So if you still remember, there are several types of forces acting on an element, or generally a metal element. There are tensile stress, there are compressive stress, shear stress. Those are basically the three kind of stress that you encounter in strength of material problems. So basically, this video will just review those properties. So let me share you the PowerPoint. Okay. So we're on chapter 6 still of Callister. So the title of this particular chapter is Mechanical Properties of Metal. So as I previously mentioned, we're going to review or discuss the engineering stress, engineering strain, the modulus of elasticity in this particular video. Okay, so this is the stress and strain measuring device. So basically the material is being stretched out by this machine, and then the output from this device is a plot of strain versus the stress. So so the slope will give you the modulus of elasticity, as you can see later. So it depends on the material, on the metal. So this property depends on the metal or the material. So from the strength of material, if you still remember, civil engineering use this data to design bridges, roads. Okay, so let's review. So these are the generally 4 types of loading that we encounter in mechanics, in strength of material. The first one is tension. So tension is defined if the force is applied perpendicular to the area of the material, to the cross-sectional area of the material. So this is tension. The first letter A is tension. So as you can see, the force is going away, going away from the center of the material. There are 2 forces, this one and also this one. And then this is perpendicular to the cross-sectional area of the material. So this is known as the tension force, and then F over the area will give you the stress, engineering stress. So right here, letter B, we have the compressive strength. Excuse me. Delivery. Okay. So, next, letter B. Letter B is, we have compression. So, as you can see from compression, the force is still perpendicular to the area, but this time, it's compressive, ano? It acts towards each other, ano? So, you're compressing the material. And then finally, we have this kind of force wherein the force acts parallel, ano? Parallel to the area of contact, A sub O. So this is known as shear force, ano? So F divided by A sub O, for this particular example, you're going to produce that would be shear stress, ano? That would be shear stress. So, di ba sinasabi sa atin sa strength of material, pag shear stress yung parang mapupunit yung material, ano? Mapupunit siya. And then, torsional, this is, I don't remember this in strength of material, probably in the latter chapter na hindi na namin naabot. This is, ang description dito ni Callister is the torsional stress. So, as you can see, the force is acting on the, the force is acting on the edge of the material. So, ito yung sa torque, ano? Probably ito yung sa torque when you have, for example, vehicles, tapos you have motors. So, nag-a-apply siya ng torque force. Ito yung torsional force. Apply siya ng torsional force. Okay, so I hope you still remember this type of stress, this type of force acting on a specific material, and then we're going to review the different equation. Nakuha niyo na ito sa strength of material. Okay, so the first one is engineering stress. So engineering stress, this is sigma, small letter sigma, Greek letter sigma, is equal to F. This is the force. This is the instantaneous load applied perpendicular, as I've discussed. This could be, engineering stress could be tensional engineering stress, or compressive engineering stress. Ano? So, force applied perpendicular to the specimen cross-section. So, ang unit nito, this could be in Newton or in pound force. LBF, no? And then A sub O is the original cross-section area before any load is applied. Kasi, sinabi niya original kasi if you still remember, pag ni-stretch out yung, halimbawa, you have tensional force, no? You have tensile force. If you have tensile force, may stretch yung material tapos liliit yung kanyang area. So, we're referring to the area as A sub O, the original area. So, ang unit nito is m meter squared or inches squared. So, ang unit ng engineering stress ay pwedeng megapascal, okay, sa SI unit, o kaya naman ay pound for per square inch, or PSI. Okay? F over A sub O, engineering stress. And then we have engineering strain, or epsilon. So epsilon is basically the change in length, or the change in the dimension, no? Delta L divided by the original dimension, or the original length, L sub O. So L sub I is the final length, L sub O is the initial length. So this is engineering strain, epsilon. Do you still remember the engineering strain from strength of material? So as you can see, kung yung kanina, ang unit ng engineering stress ay megapascal, o kaya PSI, parang pressure siya. Ito namang engineering strain, unitless siya kasi magka-cancel out yung dalawang dimensional length, no? So unitless ang engineering strain. Okay, so if you still remember, we can relate engineering stress at saka engineering strain by using the Hooke's law. So, Hooke's law, yung relationship ng engineering stress at saka engineering strain, E is known as the modulus of elasticity or the Young's modulus. So, remember this? Modulus of elasticity or Young's modulus. Okay, so let's review some properties regarding modulus of elasticity or the constant that relate strain and engineering stress, engineering strain and engineering stress. So the greater the modulus, the steeper the material. Mas matigas siya, ano, kasi hindi siya na-stretch. Okay, the greater the modulus, the steeper the material. So even if parang you can imagine is even if you apply so much force, so much tensile force, and then it is only the engineering strain or the change in the dimension is very small. So therefore the material is very hard, and then the greater the modulus of elasticity or the Young's modulus. Ano? I hope you can imagine what I'm trying to say. Ano? Or the smaller the elastic strain, basically the smaller the increase in the dimension or the smaller is the increase in the compression that result from the application of a given stress, the higher the modulus of elasticity. Ano? Hindi siya nababanat o hindi siya nakukompress, mas mataas yung modulus of elasticity. So in this particular chapter, actually, we're speaking of we're speaking of metals. Generally, ang metals have they have high modulus of elasticity. Hindi sila na-stretch. Tapos compression, hindi rin sila na-compress. As opposed by halimbawa yung concrete. Pag in-imagine nyo ang concrete mababa yung kanyang modulus of elasticity. Pag hinila mo ang concrete, actually bibigay yun, ano? So yun ang problema. Kaya pag yung mga kalsada hindi nilagyan ng bakal, eventually after some time, kasi meron ding tensile stress na ina-apply sa kalsada, nasisira kalaunan, hindi nagtatagal. So, yun yung sinasabi ng mga civil engineering na teacher natin sa strength of material. Na-imagine naman, di ba, pag semento, meron siyang compressive strength. Pwede siyang daanan ng truck talaga. Pero ang problema, hindi lang naman kasi compressive strength yun. Pag tagal, meron ding tensile strength na ina-apply yung mga dumadaang sasakyan. So, kaya bumibigay yung semento, yung kalsada pag walang bakal. Yun yung kwento dito sa modulus of elasticity. Sa tensile stress at saka sa compressive stress. Okay. The modulus is an important design parameter used for computing elastic deflections. So probably sa higher civil engineering courses encounter niyo yan. Kasi kasi ako nung college kami, yung strength of material hanggang doon lang kami sa nagbibilang kung ilan yung ginagamit na bolts, di ba? Parang hindi namin naabot yung talagang nagdi-design kayo talaga ng mga hanging bridges, no? Ang meron lamang sa bridges natin yung may dumadaan na truck, tapos magdo-draw tayo nung area nung stress, di ba? Yung natatandaan niyo. Hindi na natin naabot yung pagdi-design ng mga hanging bridges. Pero probably doon to ginagamit, elastic deflection ng models of electricity. Okay, so we're done with compressive at saka tensile forces which result to engineering stress and engineering strain. So ang susunod natin is the shear stress, no? So So, or tau. Pero as you can see, the formula is the same. F over A sub O. Yun nga lang, ang difference lang pag shear stress, yung force is applied parallel to the area. No? Applied parallel to the area. Pero yung units is the same. It's Newton, pag SI, tapos pound force, yung force. Ano? Tapos yung area, it's in meter squared or in inch squared. So, ang unit nito, nung shear stress, parehas din sa ano? Parehas din sa engineering stress. Ano? Na megapascal pag SI, tapos pound force per square inch or PSI pag ano? Pag English, no? Tandaan nyo pa, F over A sub O. Tapos yung Hooke's law naman is engineering stress is equals to modulus of elasticity times strain, engineering strain, ano? Epsilon. Ito naman, shear stress is F, still F divided by cross-sectional area, A sub O. Parang review lang, ano? And then we have this shear modulus. So yung shear modulus, this is parang ano to, analog to ng Young's modulus or modulus of elasticity. Ano? Yun nga lang sa shear siya ginagamit. So G yung kanyang symbol. Standard symbol niya is G. So this is shear stress. Tapos yung gamma dito, that's shear strain, imbis na engineering strain. Ano? So ito yung shear modulus. G. So ganun din to, no? The higher the shear modulus, the lesser the deformation, or the harder the metal is with respect to shear stress, no? So, yun yung kailangan nyo. Halimbawa, di ba, kamukha nung pinakita ko sa inyo dati, halimbawa, magdi-design kayo ng mga sasakyan, yung mga gears, di ba? Tapos may shop kayo, di ba? May shop kayo. May shop kayo. Dami pa yun. May mga shop kayo. Ito. So, di ba? Ito yung shop. Ayan. So, this is a shop, no? So, ito, pag umiikot itong block na to, so dapat mataas yung shear stress niyan. Kasi, di ba, nagka-transfer siya ng, torque. Di ba? Pag mataas yung torque. So, dapat, pag mataas na yung torque na nag-a-act dito, may possibility na ma-damage ito. Di ba? So that's why ganyan ka-significant yung yung shear modulus. So ang load kasi hindi lang naman palaging tension at saka compression. Kung minsan shearing din siya. Katulad nito, ito shear yan, no? So kaya kailangan din yung shear modulus. It's analogous to analogous to Young's modulus of elasticity. So modulus of elasticity. Okay. So I have here some table. Meron tayong table ng modulus of elasticity for different metals: aluminum, brass, copper, magnesium, nickel, steel, titanium, and tungsten. You can find this on table 6.1. Ito yung modulus of elasticity E in gigapascal. So as you can see, yung modulus of elasticity is the same unit as the engineering stress. Kasi unitless naman yung strain, engineering strain, kaya parehas lang sila ng unit. So gigapascal din siya. Pero minention natin kayo ng megapascal. So kung gusto nyo megapascal, just simply divide this by 1,000. 69, 97. Ganyan, mataas yung sa brass. Yung aluminum, medyo mababa lang. Lambot kasi yung aluminum. Ayun, magnesium mababa din lang. Steel is 207. Anong ginagawa sa steel? Bakit nagiging hard siya? Bakit nag-i-increase yung hardness niya? Tandaan niyo pa. Diba nagpapasok tayo ng carbon sa interstitial space? At yun yung taas-taas ng kanyang modulus of elasticity. Okay? Of course, tungsten. Tungsten ata, mahal naman kasi ito. Rare metal naman ito. Compared mo dito sa iron. Iron, marami talaga yan. And then ito yung shear modulus. Shear modulus in G. So pag mataas ang G, resistant siya sa shear stress. So aluminum, brass, copper, and as you can see, steel pa rin yung ginagamit talaga pag ano, no? Sa sasakyan, ano? Yung mga shop, no, sa sasakyan, mataas yung steel, ano, 83 tungsten. Ito mahal naman siguro yung tungsten. So ito na yung pinaka-practical. Nickel mahal din yun, ano? So ito iron lang kasi ito na may carbon. Kaya practical to, ano? English, ito pala yun sa English, ano? So parang 10 to the 6, this is 1 million PSI. Okay, sa English, yun sa English. Tapos yung Poisson's ratio naman, kung natatandaan nyo pa, ito yung ratio ng ano, ng pag nag-apply kayo ng tension or tensional force, di ba humahaba yung material. Nagkakaroon siya ng elongation, ano? Ang tawag natin doon, engineering strain, ano? So, yung engineering strain, ang result nun, pag humaba siya, yung diameter naman niya lumiliit, no? So, yung ratio yung change ng diameter dun sa engineering strain, yun yung Poisson's ratio kung natatandaan niyo pa. So, ito yun, ano, aluminum is 0.33 and then steel is 0.30. So, as you can see, medyo pare-parehas lang naman yung value dito sa Poisson's ratio. Ano? So, we will discuss this later. Okay. So, in the meantime, let's try to solve this example problem 6.1. So, this is about elongation, ano? Elastic computation. So, consider a piece of copper. So, this is originally 305 millimeter, 12 inches, 1 feet, ano? Tapos, this is pulled in tension with a stress of 276 megapascal or 40,000 PSI. So, what is this? Since PSI siya, hindi siya force, ano? So, this is engineering stress, ano? Hinila siya. So, if the deformation is entirely elastic, what will be the resultant elongation? So, yung tinatanong ay yung change in length, no? So, probably what you can do is, ito kasi is force divided by area, ano? Tapos this is elongation. So, probably we're going to combine the two equation. Yung definition ng engineering stress, which is force divided by area. Tapos, yung definition ng engineering strain, which is yung elongation, no? Yung delta L divided by the initial length. So ito yung meron tayong initial length, ano? We're going to combine the two. So this is the first equation, ano? Ito yung Hooke's law natin, ano? We're going to use the Hooke's law. And then another equation is the Hooke's law. So yun pala yung i-combine natin, yung Hooke's law at saka yung definition ng engineering strain. So ang engineering strain naman is change in dimension or change in length divided by original length. So this will be our working equation. Tapos ang hinahanap natin is delta L. So we're just going to isolate delta L. No? Meron tayong engineering stress. So pag in-isolate nyo, this would be engineering stress times the original length divided by E. E is the modulus of elasticity. No? So yung modulus of elasticity, kukunin natin sa table, sa table 6.1. So ang given lang sa atin ay yung stress. Yung stress natin is 276 megapascal. Tapos yung original length, 305 millimeter. Okay? Tapos galing dun sa table, yung E natin, yung modulus of elasticity for copper. So let's go to the table. So hanapin natin yung copper. So the modulus of elasticity is 110 gigapascal. So, pag kinonvert natin sa megapascal, multiply lang natin ng 1,000. Ito yon. Ano? So, just try to use your calculator and confirm that the result is 0.77 millimeter. Itong megapascal, magka-cancel out dun sa megapascal na, na dalawa. Ano? Magka-cancel out yan. So, ang magiging unit, as you can see, it would be in millimeter. So, just try to solve that equation. Ano? 276 minus 305 divided by 110. So, 0.77. Anong 0.765 or 0.77 millimeter. So, ito yung magiging resulting change in, change in dimension of the material, the one foot. Bali, haba siya ng 0.03 inch or 0.77 millimeter. Approximately mga 1 millimeter. Konting-konti lang. So, expect this in the midterm. Something like this. In the midterm. Okay. So, I hope you get this problem. Pinag-combine lang naman yung Hooke's law at saka yung definition ng elasticity. Ang kanya. Tapos ito yung sinasabi ko sa inyo yung Poisson's ratio. Kung natatandaan niyo pa. So, yung Poisson's ratio or what's this? Mu. I think this is small letter mu. So, mu is basically the negative of constriction, no? Yung niliit, yung lumiit na na dimension ng diameter, constriction. So kasi lumiit siya kaya may negative. Tapos yung elongation, this is the elongation pag nag-apply kayo ng tensile force. Kaya may negative dito kasi gusto natin yung Poisson's ratio palaging positive, no? So whether it's in the X or in the Y direction. Kasi pag bilog naman yan, parehas lang naman yung X and Y. Pero halimbawa rectangular yung beam, no? Or rectangular yung material, so iba yung X sa Y, di ba? So, pwede rin siyang constriction sa Y-axis. Pwede rin constriction sa X-axis. I hope you're getting this. Poisson's ratio. Okay, nasa table din to. Meron yung kanyang constant na Poisson ratio. Ito yung mga 0.3. Average na 0.3. Pero kung specific material, you can refer to table 6.1 para makuha niyo yung value. Okay, so let's try example 6.2. Computation of load to produce a specified diameter chains. So a tensile stress is to be applied along the long axis of a cylindrical brass rod that has a diameter of 10 millimeter. Determine the magnitude of load required to produce 2.5 times 10 to the negative 3 millimeter change in diameter if the deformation is entirely elastic. So as you can see in the solution, first, gumamit muna tayo ng engineering strain equation. So given kasi yung magnitude ng deformation, ito so 2.5 times 10 to the negative 3. Ito pala yung change in diameter. So ito yung isa, kaya negative to kasi siyempre pag nag-apply ka imagine nyo ba, pag nag-apply ka ng tensile strength, ng tensile force, hahaba yung material tapos yung diameter niya liliit. So ang tinatanong is, ano dapat yung load na yun? So 10 millimeter originally yung material. So makakalculate natin yung engineering strain with respect to the diameter. So ito yung engineering strain with respect to the diameter. 2.5 times 10 to the minus 3 millimeter divided by 10 millimeter. Ito yung given dun sa problem. So ang ating E sub x ay negative 2.5 times 10 to the negative 4. So as you can see, gagamitin natin yung concept ng Poisson's ratio. Tandaan niyo pa ba yung strength of material nyo? So ito yung definition natin. Yung second equation natin is the Poisson's ratio definition. So ang Poisson's ratio definition is B is equals to negative EX divided by EZ. So ang EZ, kakalculate natin yung EZ is 2.5 times 10 to the negative 4. Tapos ito yung nasa table, 0.34. Sa brass. So tingnan natin yung brass sa table. Ito yung brass. Ito yung Poisson's ratio niya. 0.34. So ganun lang yun. So yun, substitute nyo lang dito yung sa brass, tapos 2.5 times 10 to the negative 4. Makukuha nyo na yung EZ. So meron kayong EX at saka EZ. Ito yung EZ, ano? 7.35 times 10 to the negative 4. So ito, millimeter pa rin to. Ano? Kasi millimeter. Ito, unitless pa rin to. Ito, unitless pa rin. Unitless naman kasi yung EX, tapos yung B, unitless din. So unitless pa rin itong 7.35 times 10 to the negative 4. Tapos pag may EZ na kayo, as you can see, susunod, gagamitin nyo yung ano, yung Hooke's law. This is the Hooke's law. Ano? So EZ is 7.35 times 10 to the negative 4. Okay? Times yung modulus of elasticity. So gamitin ulit natin yung table 6.1. The modulus of elasticity is 997 times 10 to the 3 megapascal. So nandun pa rin yan sa brass, ano? Ito yon, 97 gigapascal sa brass. Doon galing yan, ano? So pag megapascal times 1,000, ito yung times 1,000. So meron na tayong engineering stress. Ang engineering stress natin ay 71.3. Tapos yung definition ng engineering stress is F over AO, or F is equals to engineering stress times cross-sectional area. Ang formula ng cross-sectional area pag a circle is pi, di ba? Pi DO squared divided by 4, or pi DO divided by 2 squared. So this is the cross-sectional area. Just multiply yung makalculate nating 71.3 megapascal. Ito yon, no? Mega is 10 to the 6. Tapos multiply natin ng area. Ang given diameter natin ay 10 to the minus 3 millimeter. No? Milli is 10 to the minus 3 divided by 2, tapos square, tapos times pi. So ang lalabas dyan is around 5,600 Newton or 1,293 pound force. No? So, okay. You can confirm these values one by one. Simula kayo dun sa simula. So ito naman, kahit tingnan nyo lang, maging negative 4. Tapos ito, i-divide nyo yung 2.5, divide nyo lamang ng 0.34. So you're going to get 7.35. So tama dito, negative, positive na siya. Confirm to, Tapos 7.35 times 97. So you have 71.295. So tama to, 71.3. Tapos finally, 71.3 exponent 6 times 10. Kailangan natin square. Tulong natin. Tapos yung 10 exponent minus 3. Tapos 2. Tapos squared. Okay. Tapos times pi. Times shift pi. So, oops. May extra akong times na sa simula. Ayun. So, 3565 pi over 2. 5599.88. So, that's 5,600. Ano? Tama. Okay. Madali lang naman, So, expect this calculation in your midterm exam. Okay, so that's it. So, after this video, try to answer your midterm exam. I'm going to post it soon. So, see you on the next video.